I have three problems here of forces at angles. In the first one, a block is getting pulled up with an applied force and it has friction. Here, a block is suspended from two ropes at equal angles. And here, a block is getting pushed downward diagonally across the surface. And we're interested in, it has friction as well, but we're interested in what the coefficient is. So in each case, what we're asking for is listed underneath. The acceleration on number one, what's the tension in the ropes, 1 and 2 for number 2, and then what the coefficient of sliding friction is for number 3. Pause the video, jot down the problems, and then we'll start in. For the first problem, with this block getting pulled, the very first step, and actually the first step on any of these problems, is to draw the free body diagram. So let's go ahead and draw the free body diagram for that block getting pulled at an angle. The one that sticks out the most is it's got this diagonal force of applied. And then as I start thinking about the other forces that are involved, it's got a weight to it, an mg value. And then there is friction, so there must be friction force kind of working against the motion of the block. And the last one is the normal force. And how big I draw that kind of depends on what's going on in the problem. Because I'm also pulling up additionally in this rope, my normal force is not going to be as long as the weight of the object. It's going to be less than, because the two up forces are what are supporting this weight. So I'm just going to draw normal force, a smaller amount, and label that. So that would be my free body diagram. The second step is to break any diagonal force up into vectors. And I can do that off to the side. I have this applied force that's really made up of a horizontal and a vertical component. And given the angle here was 30 degrees, then I can express these two sides in terms of that hypotenuse. This is FA cosine 30, and this is applied force times the sine of 30. And I'm going to use all those when I go to write my net force equations. So let's start with the net force in the x direction. And when I write that net force, it's really just equal to mass times acceleration. If I break that down line by line, the sum of the forces, what this first way of writing it is the subtraction part. Like I can say the net force is really the applied force times the cosine of 30 to the right minus the force of friction to the left, and that should equal then the mass of that times the acceleration. Notice my net force equation does not have any, I'm not filling in actual values yet, I'm just kind of leaving it as variables. That part will come later. So I do a similar thing in the y direction where the net force, or the sum of the forces in the y direction, will equal the mass times acceleration in that direction. And I kind of already know in the back of my head there is no acceleration in the vertical direction, but it's still okay to write the statement out. And we'll get to that when we plug in the numbers. We'll see that the acceleration is 0, so that's going to wipe that out. But as far as the forces go, I have two upward forces. I have normal force plus this vertical component of the applied force that we called FA times the sine of the angle. Those two are added because they're up, and I'm going to subtract the force of gravity down, and that should all equal mass times acceleration in the vertical direction. Well, that is going to go to 0, and at this point, as far as like how do I get to the acceleration, then it's really only the acceleration in the x direction that I'm concerned with. So by just leaving this all as variables, I can say, all right, if I want A all by itself, then I just need to divide mass over to the other side. So now my math becomes divide this side by mass, divide this by mass, and this expression will get me to the acceleration. Let's just kind of go through that one by one. Do we have everything we need? When I look at FA, that's the applied force. That is something they gave me in the problem. I'll kind of zoom out again, go back up to that. So they gave me the applied force of 400 newtons. So I have that. I have the angle, cosine of 30. I don't have the friction yet. So if I'm just kind of off to the side thinking, if I need to get friction, I have an equation for that. It's the mu, the sliding friction coefficient, times the normal force. Well, that's good. They gave me mu in the problem, but I still don't have normal force. So in each of these cases, it's like I'm kind of one by one going, okay, do I have enough? Or what else do I know? I have an equation. Well, do I still have enough? No, I don't have the normal force. But keep in mind, you do have normal force expressed down here. Normal force you can get to if you plug in the other things in this formula and solve. So let's just work out that math down in the net force in the y direction equation. The normal force would be, if I add force of gravity to the other side of the formula, and then subtract FA sine theta to the other side to get that normal force all by itself, it says that the normal force then should equal the force of gravity minus the applied force times the sine of the angle. All right, well, I have all that information. The force of gravity is just mg, and the applied force is 400. So 30 kilograms times 10 newtons per kilogram would be 300 newtons of gravitational force minus 400 times the sine of 30. The sine of 30 is 1/2, so that really says 400 times 1/2, or 200. So I have the normal force is equal to 300 newtons minus 200 newtons, or 100 newtons of normal force. Once I have that, then I can just go ahead and plug that in up here. So I look and I see that the coefficient they gave me was 0.2. I'm going to plug that in for mu. The normal force is 100. Plug that in for normal. And I'm left with a force of friction equaling 2/10 of 100, or 20 newtons. So I'm getting closer. Now I have a value for friction is 20, and I go back and I look through and I think I had everything else that I needed, and I'd be ready to solve. So I have the applied force of 400 cosine of 30 minus 20 divided by the mass of 30 should all equal A. I'm going to calculate that out, and we should get to the same answer. So when I dumped all that math in, I solved for an acceleration, and I got 10.88 meters per second squared. And that's number 1. In problem 2, I have this mass that's hanging by 2 different strings called a T1 and T2, and they want to know what those tensions are. Something about when I have equal angles here, I will have the same amount of tension in each rope. So that's something kind of nice to rely on. So if I solve one, I really have the tension in the other. In order to get there, though, I got to go through my steps. So step 1, draw a free body diagram. I got tension 2 out this way, tension 1 out this way, and then an mg value, or a weight value, straight down. Next, we break up forces into components, so I'll just break up one knowing that the other is going to be the same thing in the opposite direction. And I got, if this is, there's a little geometry here. If this is 20 degrees up here, then that is also 20 degrees down there, the alternate interior angle. So that's, I'm just breaking it out to the side here, and that's my 20-degree angle. So this will be T2 times the cosine of 20. This will be T2 times the sine of 20. So it's going to look the same on the other side, just expressed in terms of T1. So this is T1, this would be T1 cosine of 20 and T1 sine of 20. Now, just a little symmetry here. Since I'm talking about the exact same triangle, T2 sine 20 is really the same thing as T1 sine 20. These are identical upward. That's going to kind of help us figure out what's going on to counteract this downward force of gravity. But we'll see all that when we get to our net force equations. So let's start with the x direction. The net force in the x direction would equal the force to the right, T2 cosine of 20, and minus the force to the left, which is T1 sine of 20, and that should all equal 0, which really just tells you that the component to the right, T2 cosine of 20, equals T1 sine of 20. Well, if you have that side that's the same and the angle's the same, then those vertical sides are going to be the same. So as we move down to the y direction, I got two upward forces, which is, since I have two of them and they're the exact same, I'm just going to say 2 times T1 sine of 20. And it really wouldn't matter if I picked T1 or T2 to solve this for, because they're the exact same. So that should subtract my weight, and then I'll equal 0. So if I'm going to go solve for what this is, then I have to just add weight to each side. And that says now that 2 times T1 sine of 20 equals mg. I'll divide each side by 2. And that means that the weight divided by 2 is going to equal that value of T1 times the sine of 20. So what it really does is it gives me that upward component, and you can technically even solve for T1 just within that. If I want to get T1 all by itself, which is the diagonal vector, I just need to divide sine of 20 over to the other side. So that becomes my expression that T1 would equal, I'll rewrite it here in just a second. T1 would equal the weight divided by 2, which is, let's just get that solved. The weight was 500 newtons because 50 kilograms times 10. So 500 divided by 2 is 250 newtons divided by the sine of 20 degrees. And I'll just go ahead and calculate that out. Sine of 20 is around 0.34. So I take 250 divided by that value. And we get that tension is around 700 and, I'll just round it to a whole number, 731 newtons of tension force. So if this is 731 newtons of diagonal tension force, then this also has to be 731 newtons of diagonal tension force. So that's an example of how we can solve those forces at an angle. Again, if I did that more conceptually and just saw it as like, well, there's 500 down, so there's got to be 250 in each rope up. And from then I had my angle of 20 and I had a side of the triangle. I could then just solve for the hypotenuse of the triangle. It just depends on what they ask you to do. If they just say get the tensions, then you do what you need to get to that answer. If they say write a net force equation to solve, then we have to show that we can do that. But the reason I always get in the habit of writing these net force equations is that they are typically the way to solve the problem. They're the solution to the problem. And so sometimes you can do it conceptually all within the picture, but if that doesn't make sense, then going through this process is how you would figure out how to get to that value. All right, last problem, we got another box getting pushed at an angle, and in this case, we're shoving down into that box. So let's go ahead and visualize that force. If I was that 5 kilogram box, that 50 newtons that's coming in from this side when I draw the free body diagram, it experiences that force down at an angle. So that applied force is drawn, not happening to the box like in the picture, but from a free body diagram perspective, it's happening on the box by that outside force. And if I'm pushing that way and I'm trying to visualize the rest of these forces, then I have this additional downward push into the table. And so the normal force is bigger than it typically is. It's going to be a larger amount than the weight down because it's trying to counteract both of those downward forces that are into the table, and it has to push harder to respond to that. Now it looks like I'm shoving that box to the right, or it's accelerating to the right. So the frictional force is going to be back to the left. And that's as far as I can go with the free body diagram. The next step is to break that diagonal vector of applied force into components. So I have, just to help visualize, do it off to the side. If this is the applied force, and this is the applied force times, let's make sure this angle is correct here. In the picture, just continue this geometry here. If this was 30, then so is this. So that angle has to be 30 degrees. So I have FA times the cosine of 30 and FA times the, not here, FA times the sine of 30 for these components. Again, those will go in my equations because I can't put a diagonal force into my equations. All right, so let's write out the net force equation. Ultimately, we're interested in friction, and in the back of our head, we know that friction is mu times normal, so let's just kind of keep track of that. That's what that is. So when I go to write that in the formula, it's your choice. If you want to write it as just the force of friction in the equation, that's fine. Or if you want to just substitute it right away and write that, that's fine as well. The thing is, I don't know what normal force is, so I'm just going to leave it as that for now. So let's do net force in the x direction first. The net force in the x direction is equal to, and so I have this applied force component to the right, FA cosine 30, minus the force of friction to the left, mu times normal force, and that should all equal the mass times acceleration of the object. Again, they gave me the acceleration and they gave me the mass, so I'll have values for that kind of stuff to fill in. I'm looking for mu, so at this point I'd be like, well, I'm pretty close, I could just solve, but the only problem is if I need mu, I would also need to know what the normal force is. So I'm almost there. I have everything else I need except for normal force. We're going to get that from our vertical direction equation. The net force in the vertical direction is equal to, I have an upward force of normal minus the two forces down. So I got an mg that's pointed down, and it depends on how you want to write this. You could either subtract again, or I usually like to just combine the two forces down and put in parentheses. So mg plus FA sine of 30. So by putting those together in parentheses, I'm saying take the normal force up minus these two forces that are both pointing down, and it's not accelerating in that case, and that equals 0. Therefore, my normal force is simply equal to the weight of the object plus FA sine 30. Well, I can get a value to that because they gave me the mass. And the problem is that the mass is 5 kilograms, so 5 times 10 is 50 newtons. And the applied force was also 50 newtons, just as a coincidence. It's not related, it's just it's what they picked for the problem. So I have 50 newtons times the sine of 30, or times 0.5. So that's 50 plus 25. So I have a normal force of 75 newtons when I go to solve that math. Now, I have a number that I can use up here. And at this point, I have everything I need to get mu all by itself. So my algebra steps might look different than yours, but I like to get the negatives and everything just kind of all into a positive statement. So what I would do is I'd add this to both sides to get rid of it on that side. And then I'm going to subtract MA to get it over to the other side. And last step, if I want mu, is I'd have to divide by normal force. So just kind of showing you each step all in one statement. And so boom, boom, and I'm going to divide all of this by my normal force. So I'm going to rewrite that a little cleaner. This final expression is going to say mu equals FA cosine 30 minus the mass times acceleration, all divided by the normal force. And at this point, then it's just a matter of plugging in your numbers. So go ahead and calculate that out, and hopefully we'll get to the same answer. So I got that would equal around 0.44. And again, no units on a coefficient because it's a unitless ratio. So that is the final solution.